So hi everyone. So this is the first lecture in our whole course, and the first we'll start with the mathematics. As you already know that I am in love. I'm in love with mathematics from head over heels. So we'll start with this. Okay. So before starting this, let me just tell you some real world scenarios, and then we'll try to map those into maths. And basically, what we'll do, we'll take a real world phenomenon or real world thing, and then we'll try to model it mathematically. That should be the approach, and then we'll name the things. Whatever the template I told you, I'll be following. We'll take a problem, and then try to understand the problem, and after that we'll mathematically model the problem. Once we're done with the modeling, and then we'll give the names. Okay, so what I'll do is I'll take let's suppose a real world problem of age is somehow related to height. Okay, let's suppose if there is a newborn baby, so it has a, let's suppose it has age 1 years, or maybe usually people start with 0 years, something with that. So if you see this age, so till let's suppose 10 years of age, you will see some growth in the baby, and similarly when you go from 10 to 20, again you will see some growth. Then after 2021, you will see it has somehow tapered off. The height of this person, or height of the baby, was initially, let's suppose, some uh, 75 centimeters or something, and it will slowly increase till, let's suppose, the baby now grew, it became an adult, and its age is now 175 centimeters. His or her age is 175 centimeters, something like that. So you can see that with the age there is some relation with the height. Okay, I cannot say causation, cause is a different thing. This age might not cause the height, but there is some relation if you see. So with the age, height also increases. Similarly with the weight. Okay, so age also has somehow some correlation or some relation with the weight. And again, if you see day to life, right now we are in Bangalore and it's burning hot in Bangalore. So what happens here is, so if you see the whole year, so in this year you will see fluctuation in the temperature, and sometimes that's how we have considered seasons. We have winter, and then probably we have summer, spring, and these seasons. Okay, we have divided the whole year into seasons. Why? Based on the temperature, and there is this cyclic process going on. So what I am telling is basically, so there are two quantities. So if you see in here, so I took age, it had some correlation with height. Similarly, temperature had some relation with the time of the year. Okay, if you see these sort of phenomenon, so many of the real world phenomena fit into this template. Okay, so what is the template? Again, coming back, template is that we have a quantity. We have, let's suppose, quantity 1. So we have quantity 1, and then we have quantity 2. Quantity can be any physical quantity. So okay, if you have any questions regarding what quantity is, we can also define that. But here I assume that you know what quantity is. Okay, quantity is anything that we can measure. So I told you that there is age of humans. It has some relation with height. Similarly, this date has some relation with temperature. So we have some correspondence. If you know one thing about a quantity, you can say something about other quantity, and based on the relation they have. Okay, that's where we in mathematics we bring in these functions. Okay, what functions basically are? They try to map this template, because many of the real world problems, if you see, so a real world phenomena, they have some relation. One quantity has a relation with other quantity, and maybe some a lot of different quantities, when they combine together, they produce some effect. Okay, these are the phenomena that you will see in the nature, in the real world. A lot of things that will happen will fit into this template. Let's suppose with your even marks, let's suppose the amount of hours you put into your studies, and I think there is a direct correlation with the marks you'll get in the exams. Okay, and similarly, let's suppose you can see salary. Somehow it has a relation with the highest education you have got. Okay, that's the salary you got. Many of these problems, like, this is just a template. What we are following is template, and now we want to mathematically model it. So that's what beauty of maths is. Math is now not constraining us to this just a physical phenomenon. So what maths does is it will club all these physical phenomena. While the basic rule is that some quantity has a relationship with other quantity. There are maybe, or it can be like this. So there can be n number of quantities. They have relation with n different quantities, but there is some relation, there is some correlation, and knowing one thing will tell us something about other, knowing of other quantity. Let's suppose if for an average human being, if you know let's suppose age, if you know the nationality, you can somehow guess the height because you know that age follows a particular distribution. Okay, if many of these problems follow this sort of template, so we try to mathematically model all these problems together. So see how many problems we can solve. I think hundreds and thousands of problems like this will be following this sort of template, where we have some quantities and they'll have dependence on other quantities and they'll somehow affect each other. I am again underlying this fact that it cannot be causation, or it may not be causation, but there is a relation. Somehow if you know one quantity, you can sort of guess and it gives you some information about the other quantity. Okay, and a lot of problems follow into this template. What maths does is, so maths will club all of these problems together, now, irrespective of what problem is. So we'll come up with a generic framework. We'll come up with a generic modeling. So in that model, we'll fit all of these problems in one go. And if we solve one thing, so now what we are doing is we'll club all of these problems together. And there will be hundreds of problems like this, where you will see one quantity having an effect on another quantity. Knowing about one quantity will give you some knowledge about the other quantity. So if you have this template, now what we'll do is we'll abstract the details out. So whatever the details there are, we'll not look in the details. Okay, this quantity age. Now what math does is it gives us tools. So it will give us a tool, this age, date. Now these are all physical quantities. Now instead of this physical quantity, what I can do is I can write some abstract symbols. I won't care about the quantities now. अब मेरा यहाँ पे point ये नहीं है कि मैं quantities देखूँ. So what I'll do is मैं एक काम करता हूँ, ये सारी की सारी जो चीजें हैं, so I'll give them a variable name. I'll say, let's suppose there is this x. For this variable, let's suppose give this value y. Because you see the template, we had two quantities. We'll restrict our discussion for the two quantities. First we have one quantity and then we have two quantities, and slowly we'll progress. अब ये सारी जो प्रॉब्लम्स हैं इनको मैं कैसे मैप करूंगा? I'll abstract out the details. अब मुझे ये फर्क नहीं पड़ता कि एज का हाइट के साथ क्या है, डेट का टेम्परेचर के साथ कैसा लेना देना है. I won't care about that. I'll see whatever is this. So I'll have a quantity x and then I'll have a quantity y. So somehow I know this x is somewhat related to this y. ये जो x है ये किसी तरह related है y से. So if I know something about x, I'll know something about y. Okay. So ये x को मैं कुछ value दूंगा and correspondingly I'll get a value of y. So this is what we call functions in maths. So what functions are basically the rules that describe how one quantity depends on another. A simple definition. I won't go into mathematical details, and probably you will feel it really easy. So when I start these things, people feel it really easy. But at the end of this, you will have to read a book and then you will understand everything that goes underneath. Usually you will see in mathematical books, you will see something written as this. Function A goes from A to B is this, and they'll have a definition. But underneath the hood, what they try to convey is, they try to convey this. So what a function is? Function is a rule. So a function is a rule. Okay, what is this rule? That describes how one quantity depends on another. I hope everybody is comfortable with this. Is everybody comfortable with this definition? Or do you want to argue something? अरे कुछ तो बोलो. हाँ ना बोलो. Okay, at least raise your hands, or if you are not comfortable speaking, तो अपना hand raise करना. So again going back, giving the thing is that we started with some problems, real world problems. हमने यहाँ पे देखा कि one quantity has an effect on the other quantity. So if you have quantity 1, it impacts somewhere, it depends on some quantity 2. So now in mathematics, what we'll do is we'll abstract the details. We won't care about what the problem underneath problem is, but it has the same structure. The structure is that one quantity somehow depends on other quantity, and one quantity somehow affects the other quantity. That's what we did. Now we introduced these variables. Maths is not difficult because people sort of have to learn a lot of stuff. Maths is difficult because people get confused about symbols. It's like poetry. I always tell this, mathematics is like poetry. So poetry is not difficult because of the words. So basically what poetry is, you have to know the gist, what is the poet talking about. That's how maths is also. So maths is not difficult because you see these lot of rules and stuff like that, but it is difficult because people usually don't know what the guy is talking about, or the mathematician or the writer who is writing the thing, what he is talking about. Okay. So now we define a function. So function is basically a rule that describes how one quantity depends on another. So now we'll see how to evaluate these functions, or what to do with these functions. Now we had a real world problem and we abstracted it out and we came up with something called as functions. Okay, so functions in this, you'll usually see two types of things. You will see this x and y in if we have two quantities where we have this one quantity depending on another. So we'll call this x as independent. Both of these will be called as variables. So in mathematics, variable is anything that usually changes its values. Okay, it doesn't have the constant value. I won't go into the mathematical definition. I'll just give you the definition so that you understand the intuition first, and slowly we'll try to build the maths around it. So this x has been, now this is this quantity. Let's suppose age, date, amount of hours you put into the study, and salary and stuff like that. This is x, and then we have this y. So we call this x as independent variable. So this is an independent variable, and this is a dependent variable. And why do we give them such names? Because let's suppose you know something about x, and then you can correspondingly tell something about y. So somehow you can see that x can be chosen independently, and now the value of x somehow forces y to give the value. Okay, so let's suppose in this age and height case. So if you somehow take the age, here you are independent to choose any value. So you can tell, let's suppose 10 years of age, 15 years, something. But whatever you choose in this age column or in this age value, so this somehow restricts the number that you will get in the height. Okay, so this over here, that's why it's called the independent variable x. Why? Because you can choose the value independently. Nobody restricts you from choosing any value. But this y, once you chose this value of x, okay, now this y depends on x. So now this y, the value of y will get some defined value, because depending on this x. That's why you will sometimes you will see this y is equal something of x. Okay, somehow it depends on the x, and this y is sometimes also written as f of x. Okay, and there is some values, and there will be some quantities of x in here. This is what a function basically is. So function, simply again coming back to functions, a function is just a rule that describes how one quantity depends on another. Okay, there are a lot of problems in real world that follow this template, where we have a quantity and that it depends on other quantities. I think I'll say like 90 to 95% of the phenomena that you see in the world can be mapped like this, can be given such a rule, because they are deterministic process. And now let's see what makes a function. Okay, now you can see that we'll have a set of values, okay, and then we'll have a set of outputs. Now you'll have values, let's suppose 1, 2, 3, 4, something like this, and they'll be mapped to something 5, 6, 7, 8, 9, something like this, whatever it is. Okay, so one can be, let's suppose there is some rule in between. So this is, we'll call a function. So this one will be mapped somehow, let's suppose, to 5 by this rule. Okay, it will go through this rule and it will map it to 5. This 2 can be mapped to 7, and this 3 can be 3 will be mapped to 6. Consider this function is a machine. It takes something as input and gives something as an output. Okay, now there are some restrictions mathematicians put. So what is the restriction? The first thing is that this machine should be deterministic. So what I mean by determinism, so this machine should be such that, let's suppose if 3 is mapped to 7, this 3 should not be mapped to any other number. Okay, so that means if you give an input, I'll call this input or independent variable. Well, I'll call this output or dependent variable. Okay, so now you have this machine. You will put, let's suppose, 1 in here. You will get 5. The mapping should not be like this. So 1 should, let's suppose, give 5. If 1 gives 7 also, then it's not a function. Okay, so functions should have determinism. So this is what I mean by determinism. So if you give value 1, it should give 5. If you next time give value 1, it should again give 5. It should not be 7 or something. So that means that one input should not be mapped to multiple outputs. But other way can be done. So but what can be, this is not a function. So if we have a function, if we have something in which we have a single input mapped to 2 outputs, that's not a function. So but other way is a function. So by that I mean that if we have, let's suppose, 1, it can be mapped to let's suppose 2. And if we have some input 3, it can also be mapped to 2. So this is a function. Do not lose the sight. What are we dealing with? We are dealing with real world problem. Now what I said is that there are a lot of problems that have the same template. Now I have abstracted out the details. I don't want to particularly solve your problem. Now what I want is I'll solve all the problems at once. अब मेरा काम ये नहीं है कि मैं अब एज को हाइट ये सब इनकी फंक्शंस को अलग से पढ़ूँ. So what I'll do is I'll form a set of rules. I'll form a language for all of these problems together. And if I have to solve these problems, it will become really easy. किसको ये point समझ आया of maths? Isn't this beautiful? How many of you understood this beauty? So the power that maths gave you. Otherwise you had to handle all of these problems separately कि ये उठाओ और इसका relation देखो, ये उठाओ इसका relation देखो. That's what maths does you. Maths gives you a lot of tools, and now we are slowly developing a language. Okay, we are slowly and slowly developing language. So हम लोग अभी क्या कर रहे हैं, हमारे पास एक input था, हमने सोचा कि इसको map करते हैं to some output. So now we are putting constraints. We are saying that this function should be deterministic. Okay, so if we have something like this, if this one is mapped to 5 and this one is mapped to 7 also, then we have some uncertainty involved. There are problems which will follow this template also. कुछ ऐसी चीजें भी होंगी जहां पे हम लोग कुछ एक चीज करेंगे वो एक आंसर देगा, सेकंड टाइम विल डू इट तो कुछ और चीज आ सकती है. दैट विल डील सेपरेटली प्रॉब्ली इन प्रोबेबिलिटी और समथिंग. ओके, बट हियर वी आर फिक्सिंग आवर टेम्पलेट. हमारे पास टेम्पलेट क्या है कि वी आर पुटिंग रिस्ट्रिक्शंस नाउ, कि हम लोग ऐसी प्रॉब्लम्स को डील करेंगे जहां पे मेरे पास क्या होगा, आई विल हैव one input, it should not have corresponding to outputs. One input means it should only have one output, but this output too can be associated with multiple inputs also, because this is not this does not break our rule of determinism. Let's suppose input 1 दिया, it gave me 2. Second time I gave 3, it again gave me 2, but again जब मैं 1 देता हूं तो वो फिर से 2 देगा. So again coming to this determinism. So what I mean by determinism is that the value should be replicable, the process should be replicable, the whole thing should be if I gave this one as an input and I have this machine which I call as function machine or something, so this is giving me some output 2. Second time if I give this one, the value should be again 2. Okay, it should be reproducible. That's what basically science is. Okay, what is the basic definition of science? So science basically means when you do a thing, okay, it should be reproducible. You should be able to reproduce it. If you are not able to reproduce it, then it is not science. It's some magic or something, or probably witchcraft, whatever it is. Okay, so here if you do the steps, the same steps you did, let's suppose you had one process, you did something and you got some output. Okay, you had a process and you got some output. If you again perform the same thing, perform the same procedure, and you got the same output continuously, that's why we call it science, because it's reproducible. If somebody claims something and other person came and he does the same exact steps what was earlier done and he got the same output, then we call it this experiment was reproducible, and that's what makes it science basically. So similarly, that's what science has, the determinism. So in that we have a machine, and in this determinism the machine should be given an input and it should give a specific output. I hope this is clear. Okay, now the first restriction we put on these functions is that one input should be mapped to only one output. Does magic exist in science? There is a question by Mahmood. Does magic exist in science, or does science believe in magic? So actually scientists don't believe in magic. Why? Because they try to understand the phenomenon. There is something going on inside, and which probably basically it boils down to the definition of magic, what magic is. So magic could be you don't understand the phenomenon and you feel something happened which your brain cannot comprehend. Let's suppose for a guy who is who died 200 years ago, if you show him this phone, by help of phone I can call somebody, he'll find it magic. Why? Because he does not understand the thing. I hope that this makes the definition of magic like that. That's how I see the magic. Magic basically means which will puzzle me somehow. I won't understand the thing, what's happening, and then the only explanation I'll have is this is magical. I cannot explain the thing that happened. Okay, but once you develop the understanding, that's what science basically is. It tries to demystify those things. It goes away from the magic. Okay, if you have something, we try to explain the phenomenon. I hope I gave you the answer. If you have something, you can again ask. But again, we are putting now restrictions is that one input is only having the one output. Do not get confused like this. Key, there will be one-on-one mapping. Like let's suppose we have 1, 2, 3, 4, and there will be A, B, C, D, and we'll have mappings like this. By this statement, I do not mean this. What I mean is, for one input, there should be only one output. It can be like this also. Okay, you can see it over here. So 1 is mapped to A, 2 is also mapped to A. But you can see that clearly. One input only has one output. 2 only has one output. This is not a function. If we make like this 1, 2, 3, 4, A, B, C, D. If this 1 is mapped to A, 1 is mapped to B. Now you can see that one input got 2 outputs here. So this is not allowed. So this basically is allowed. That's putting one restriction. Now if you see this, it takes some values as an input and it gives some output. Again, let's mathematically name them. There are standard names for this in mathematics. So whatever input is taken by the function, this is called as domain. This is called as domain. And whatever output is given, it's called as range. Okay, now just giving the names to these concepts. Usually people give the names first and then they explain the concept. Now you see that a function is nothing but just a mapping, just a rule which maps one quantity to another and shows how the dependency is. And it takes something as an input and gives something as an output. Okay, now what we see is this input is basically, we call it a domain. And this output, we call it a range. And this is our function. And now this is how I wrote it. Now I'll mathematically write it. So what mathematically how we write it is, instead of this function, I'll probably write a symbol like f, g, h or something. I'll write a symbol like this. And for this, I'll write some capital letters. Because usually domain is also numbers and range is also numbers. It is not necessary that there will be numbers. They can be something else. Okay. Now see, I'll also abstract out the details. So here I'll write this as f. Okay. It takes its input as this domain. I'll call it d, and it gives us some range. This is what you will see in the textbooks. So basically, how do we read it now? So we have a function f which is defined on domain d and which has range r. This is how it is defined. And then we'll give a definition of the function, how the function behaves. I hope that you understood this detail at least now. So how many of you understood this part? Now you can clearly see that by using mathematics, we are going away from the real world and we are abstracting the details out. Why are we abstracting? Because it gives a power to manipulate the things then. Okay, so once we have defined these things, then we'll sort of have operations or do something, and it basically will be applicable to all the problems that we are solving underneath the whole stack. So there is a whole stack. The first is that we have a real world problem. Now we are defining some symbols. Okay, and after this, we'll define some operations also. Now you see this, we'll have discussion on this domain and range. Okay, this domain and range, if you see this, we have a function, we have this function f. Now I'll write a function f, and I have this domain which goes inside and it gives some output that I call as range. Now both of these, I won't care about order, what is the order of the elements that is there. I won't care about the order. And second thing is, I won't care about the duplicate elements. Probably I'll remove them, duplicate elements. This should not be abstract, so this should be well defined. Well defined. So this domain, this applies to both of these things. So whatever domain is, I don't care about the order. I can say f of 1 gives me something or f of 2 gives me something. There is no ordering in this. Okay, this is basically some bunch of numbers. Okay, or maybe it will be a pool of numbers. Similarly for this, it will be a huge pool of numbers. So I won't care about the order. I won't care about the duplicate elements. If duplicate elements are there, I remove them, and it should be well defined. So this we'll have a discussion over. What is this well defined? Why do we introduce even these terms? Why do we introduce this order, duplicate elements, well defined? Why? And let's first have a discussion on this. So let's suppose this function it takes 1, 2, 3, 4 as an input. Okay, this is a bunch of numbers and it gives us the output some other numbers. Let's suppose 3, let's suppose 1, 4, 9, 16. These are the numbers it gives us output. So this is my input. Basically, this is my domain and this is my range. This is my input, this is my output. Now if you see that, if I again write one over here, so I don't care about this one over here, I can just remove it, because in mathematics I try to write the things succinctly. Okay, that's why here the duplicate elements I can remove. I don't care about these. And second thing is order. I can write it like this. I can write it 4, 3, 2, 1, something like this. I don't care about the order also. But this is my domain and this is my range, and then I'll have a mapping. Okay, so this is my domain. So I have domain 4, 3, 2, 1, and my range is 1, 9, 4, 16, something like this. And there is a function over here. So this function maps this input to this output. So this 4, let's suppose, is mapped to 16. Okay, this 3 over here is mapped to 9, and this 2 over here is mapped to 4, and this 1 over here is mapped to 1. Now if you see this, so this domain and range, I define certain properties. The property thing is the order should not matter. Okay, I can give these elements in any order. And the second thing I said is duplicate elements, I don't care about these things. If there are duplicate elements, I won't care about them. And third thing is well defined. We'll have a detailed discussion on this. So what mathematicians named the thing with these properties, they named it a set. So now I'll call it a set. I'll say this domain is a set and this range is also a set. Okay, probably a set of numbers or whatever it is. So it goes from set A to set B. So what is a set? So set is a well defined collection of objects, collection of, let's suppose, some entities. Again, we're abstracting from numbers. Now you see that how mathematicians deal. They don't work with real problems. They'll abstract all the details. Now here we were working with set of numbers. Now I have written a well-defined collection of entities. We'll have any entity. It can be a number. It can be a physical quantity. It can be names. But the thing is, it should be well-defined. And then order should not matter. A well-defined collection of objects where order does not matter. Where order does not matter. Where order does not matter. And third property that we saw is that we remove the duplicates. So no duplicates are allowed. Okay, so here you see that it should be well defined. Again, I did not tell you what well defined means, but I told you these two things. Order does not matter here, so you can have any order. So this basically means if I have elements like 1 2 3 4, so in set theoretic notation 4 3 2 1, this both are equal, so these are equal sets. So what I am saying is, as set in that order is order does not matter. If I write something like this 1 2 3 4 1, this basically is equal to 1 2 3 4. This is equal. So why am I again going to the sets? Because now I told you this function is defined on a set. So it goes from set A to set B, or set of inputs to set of outputs. Now set has its definition. Now let's see what this well-defined means. Well-defined means there is a particular definition. That this should be objective. Okay, this should be, what I mean by objectivity is that well-defined means it is defined same everywhere. Let's suppose I'll take few examples. I'm taking an example of 100 meter. Okay, I wrote 100 meter. So let's suppose Ejaz Siddiq is in some other country, we're in some other country, and other people are probably in other parts of the world. This 100 meter will be perceived same everywhere. So okay, if I give you 100 meters of, let's suppose, cloth, so if I measure it here, so if I send it back to, let's suppose, China or somewhere, so again, if they measure it there, this 100 meter is well defined. So everybody has the same definition of this 100 meters. It's well defined. Okay, and some other quantity, let's suppose some matrix. So the amount of data I'll be using while transmitting this, let's suppose I'll use some 2 GBs of data. Okay, so now I'm quantifying these details. So when I quantify these details, whatever I understand by this, you also understand the same. This is called as well defined. So those things are these things have definitions, proper definition. And then there are things which are not well defined, which are way abstract. So what are these? Let's suppose beauty. Let's suppose to me one person will be beautiful, to you other person will be beautiful. So let's suppose if I call person A as beautiful, probably for other people he might not be beautiful. So for me the definition of beauty will be based on, let's say, physical looks or the way he speaks or whatever it is. So maybe some other people have some other underlying features, what they see, what they call beauty. So this beauty is not well defined. Maybe intelligent. So this intelligent is also not well defined. That's why these are abstract things. Okay, and these sort of things you get these definitions from your society. Okay, and usually in subcontinent, people with white skin tone or people who usually are a bit taller, maybe have some good physical features, they're called as beautiful. Okay, and maybe some people, some in some other area, people with, let's suppose, short height, black, they'll be called as beautiful. Okay, it depends on it depends on how what society has feed you into the head. So that's why we call them, these are not well defined. And in maths, we usually don't touch these things. We can touch though, but as this is not objective. Okay, as it depends on the basically that there is a code that beauty lies in the eyes of beholder, whoever sees it. Okay, that's how they perceive the things. But there are some well defined things. Now set, there should be well defined entities. It should have definitions. If I tell you set of names, okay, the names are well defined. I'll tell in our class we have, let's suppose, set of 15 students. Set of 15 students which include Arshan, which includes Mahmood, Sohail, Ejaz, whatever. Okay, and it is well defined basically. It's not abstract in there. So if you come up with abstract terms, then we'll not call it a set. I think this well defined is clear. This order doesn't matter and no duplicates allowed. Are all the three properties clear regarding the sets? Okay, now coming back, let's zoom out our lens. We were defining functions. So functions, we defined it as, it is some symbol f and it's a rule which maps one quantity to another. It shows how the dependency is there, how the dependence of one quantity, how one quantity depends on other quantity. That's what we saw. And now we saw this domain and this range. They basically are from sets. They should be well defined. You should not say, okay, I have a function which will take beauty as an argument and then it will give me something else. Okay, there can be abstract quantities which depends on one. Maybe let's suppose beauty, it can have something to do with intelligence. And now again, intelligence is an abstract term. The thing is, you cannot properly define it. For some people, a guy with a lot of knowledge or a lot of memorization power may be intelligent. For some other people, he might not be intelligent. For some people, intelligence can be the number of exams you have passed or the number of marks that you have got. But for some other people, intelligence can be entirely different criteria. It may the measurement tool will be different. So we won't be dealing with these abstract quantities. We'll be dealing with well-defined objects, well-defined entities. That's what we call as a set. So this function now, this function goes from one set to another set. So it goes from A to B. Okay, that's how I wrote it. A function goes from set A to set B. This is one notation of writing it. Now I have to define this function if I write it mathematically. So how do I write it? Now you know that it goes from one set. Set can be written like this, 1, 2, 3, 4. Or succinct way can be set can be written like this, 1, 2, 3, 4. Howsoever you write it. So in maths, do not care about what things are written. Try to see what are they conveying, what are they trying to convey. Okay. Now there can be other form also. I can write, for example, x, and x is less than, or I can write this x such that, this is called as such that x is between 1 and 4. Both of these mean the same. And now people have named this. I think one is called as a roster form and another is called as set builder form. I don't want to get into those like whatever they named it, but I think that you got the concept. We have a set. Now we again are bringing the mathematical lingo. How to write the set now? So usual representation of set is like this. So you usually write set like this. If you have the numbers which you can count. Okay, if you have countable sets, or which we call as finite sets, in which the elements are finite, so you can write it like this. Or maybe other example is like this. You can just mention the property they have. Okay, and sometimes you will write it, if you have a set of natural numbers, you'll write the x such that x belongs to natural numbers. So basically this is equivalent to 1, 2, 3 and so on. Okay, here you enumerate the things. Okay, and here you define the common property. Now you saw the functions. Now we have function f, it goes from A to B. Okay, now we had discussion on this function, we had the discussion on these two things, and we can write this. You can write this now. So A probably will say that A is a set, or maybe, and then we can define A is a set x such that x belongs to natural numbers. And similarly we can write it for B also, A and B. A and B are sets such that they follow this. Now we had discussion on this and this also. Now we'll have to have a mapping. The mapping is easy. It's defined by the equations. It's very easy. So if you understand this lingo, so this sort of is hard part. This is hard to convey to the people. When you have a real world problem, you have one quantity depending on another quantity. Now in this quantity, it can take a lot of values, and we call this one set, and it goes to other set. So now I have defined a function. So what I'll do is I'll take a simple function. I'll take a function of square of numbers. Okay, square of numbers. Square of numbers is a function. So what it'll do, it'll take an input, or what I'll call a set maybe, and then it will give me an output. Okay, what I'll write is I'll write function f goes from natural numbers, and it again gives natural numbers back. Okay, let's suppose we will restrict our domain and our range to natural numbers. And what is the function? This function f of x is defined as x square. This is how you will see it in the books. Usually this is how it is written in the books. F goes from natural numbers to natural numbers, and where f of x is defined as x square. Now this is a whole description. If I give it f of 1, so you'll write 1 square, that is equal to 1. If I write f of 2, this is 2 square, that's equal to 2. Okay, now you can see that if you have this 1, 2, 3, 4, 5, so this is my domain, which I call a domain. I said this goes from n to n. Now again here there is n, so 1, 2, 3, 4 and so on. So now you see that if I square 1, you will get 1, but if I square 2, you will get 4. You will never get this 3 and 4 in natural numbers. That's why this set is called as codomain. This set is called as codomain. Okay, now you saw that this 2 and this 3 never got a mapping. So they do not got any mapping from this set. But the way the function was defined was from set A to set B, or set of natural numbers to set of natural numbers. But many of the natural numbers did not got any mapping. So this 2 and this 3 did not got any mapping. So this is allowed in functions. Okay, so all of this set is called as codomain, from which it is defined. So what is the range then? The range is only the set of outputs. What are the output that we got? We got the output as 1, we got output as 4, then 9, then 16. Many of the numbers are left alone. They have no mapping basically. So that's why all the numbers together are called codomain. The numbers that actually got the mapping is called as range. How many of you understood difference between codomain and range, and why is it required? Why do we require two definitions? For the mathematical simplicity, sometimes called as syntactic sugar, because if I have to write f goes from natural numbers to something, and f is defined as f of x is equal to x square. Now I know that many numbers will be left out, so I'll have to write it goes to natural numbers except 1, except 2, except 3, except 5. So better than this, I won't write it. I'll just write it goes from natural numbers to natural numbers. Okay, so this I'll call my domain. This I'll call my codomain. I won't call it a range. And then I'll call separate thing a range. Range basically is what are the actual values that I got. How many of you are you clear? Why do we introduce codomain? Why is there a need even? Okay, the need is that when we sort of want to define this range, we're good enough when we have range only. अगर हमारे पास सिर्फ output होता then we're good enough. But the thing is, when you define this, you have to again write it. You have to again introduce some more symbols. So better to write this n. Then we'll say it's a codomain, and whatever the outputs that actually we got will be called as range. Okay. Now here, if you see this, these numbers, if you see this 1, this 2, and this, let's suppose this 1, this 4, this 1, 2 is called as pre-image. Maths is more about learning the lingo. So we're right now understand the language of the mathematics. You understand everything at this. Just I'm giving the names to these things. So this 1 and 2 is called as pre-image, and this 1, 4 is called as image. Okay, so I told you what is range. So range are the elements which have an pre-image. They have pre-image. Okay, they have pre-image in this domain. Okay, the elements which do not have pre-image, they also come in codomain. Range plus those elements which do not have pre-image make the codomain. Okay, there are a lot to discuss. So we discussed about this f, we discussed about this a, we discussed about this b, we discussed about the mapping also. How many of you are clear till this? किस-किसको clear हुआ ये चीजें? Okay, so now what is not a function? That's a question. मैंने अभी तक तो इतना बोला कि this is function, this is function. So what is not a function? Can I write a mathematical expression which is not a function? मेरे पास ये होगा, let's suppose f of x is equal to x square plus 3. Okay, मेरे पास ये function होता है f of x is equal to x plus 3 plus let's suppose 3x or something like this. Okay, this is also a function, this is also a function. What is not a function? How do you even test if it is a function or not? So the only thing that you have to care about is there should not be two outputs corresponding to a single input. Now I'll write it in different phases. So I can write function like this. So in the set notation, I can write function like this. So let's suppose I have this 1, 2, 3, and 4. So this is mapped to 1. This basically is square function, x square. 1, 4, 9, and 16. So one representation can be like this. I can write function like this. So I'll write 1, 1, 2, 4, 3, 9, 4, 16. Okay, so this is also a representation of function. This is how I can write a function. And there you know this over here, the order matters now. The first element is the input. So this is input. That's why this is called as ordered pair. This over here is called as ordered pair. How many of you know all of these terms? I hope that most of you know all of these terms. So you guys know all of these terms. I'm just naming them, putting them in right context. So if you see this is called ordered pair, why is it now called ordered pair? Because you see that if I just flip the order, if I write 9, 3 instead of 3, 9, all hell will break loose. Why? Because I'm saying that 9 gets the output as 3, but it's the other way around. It is 3 gets the output 9. This is one representation of what a function is, how can I write a function. But now this has problems. So if I write it like this, if I write 1, 1, if I write 1, 2, now it is not a function. It is no more a function. Because I have seen that this one input, this one is corresponding to two outputs. It's corresponding to input output 1, output 2. So what mathematician has done is, so they have defined this as a relation. Okay, again going back, so this is a relation now. So I told you that a function can be written like this, but there is a problem, there is a subtle problem. If you see, I told you these are ordered pairs. Now what I can do is I can write something like this also, 1, 1, 2. Okay, so I can define this mapping. I said that a function is a rule. It's a rule. So I can write this. This is also a rule. Okay, there is also some relation between this. 1 is mapped to 1, 1 is mapped to 4 also. or one is mapped to some other thing also. So what I will put is, I'll put these things in here. So I call the relation. Okay, so what is the relation? If I have a set A and I have a set B, so set A is like 1 2 3 4, and set B is, let's suppose, something else, A B C D. If I took all these things, so if I took all these things together, I can write something like this. I can write 1 comma A, I can write 1 comma B, I can write 2 comma C, and so on, like this. This is a relation. Okay, this is a relation. So if you see this is the relation, because one is related to A here, one is also related to B here, then 2 is related to C here, and these two elements are not related. Okay, that's how mathematics defined relation like this. They said any mapping, if you take set A and if you define any mapping to set B, that's called a relation. Okay, now if you see, if you have to have all the mappings, what you can do is, you can map this 1 to A B C D, you can map this 2 to A B C D, you can map this 3 to A B C D, you can map each element of this to every element of this. We can write it like this: A can be mapped to every element of it. This is called as Cartesian product, a Cartesian product. So we have set 1 2 3 4, this is set A, and we have set B, that is A comma B comma C comma D. If we put all the ordered pairs together, okay, if we put all of them together, 1 comma A, 1 comma B, 1 comma C, 1 comma D, then 2 comma A, and similarly for all of these, until this 4 comma A to all of this 4 comma D. If I put all of these together, this is called a Cartesian product, because I am defining all the possible mappings that are there. So I am defining how A can be mapped to this set. This one can be mapped to A, B, C, or D, howsoever. So if I put all of these ordered pairs together, this is called as Cartesian product. Now coming back to maths. So how I define relation? I said if I define any relation. Now can I say that a relation is a subset of Cartesian product? How many of you agree on this point? I can say that relation is a subset of Cartesian product. Because that you can clearly see, I can define any relation, but in Cartesian product what I have done is, I have defined every possible mappings. I have defined 1 to A, 1 to B, 1 to C, 1 to D, similarly 2 to A, 2 to B, 2 to C, 2 to D. Okay, similarly what I have done is in here, so I said a relation is, I can take a particular instance from that. I can take 1 is mapped to A, 1 is also mapped to B, 2 is mapped to C. I can take some elements of this. That's what I mean by subset over here. So the symbol subset is written like this. A relation basically is a subset of Cartesian product. Okay, now coming back to functions, I'll put all of these things together at the end. Okay, I think we have some 10-20 minutes left in the class. I'll put all of these together once. Please bear with me for maybe you can see that material is going here and there. We started with functions, we're going in sets, relations, but all of these things will make sense after a while. So you see that now this function basically are special type of relations. Okay, so the functions, these functions are special types of relations. Types of relations. Now you know that this relation is basically a Cartesian product, okay, in which if you have an ordered pair A comma B, and if you have second ordered pair A comma C, okay, if you have these two ordered pairs in that relation, that means C should be equal to B. How many of you understood this vaguely? I'll explain this if you do not understand this. So what I'm saying is, if this is present in the relation, and if this is also present in this basically forces me that this C should be equal to B. This tells me that if 1 comma 2 is in the relation, then if I say this 1 and there is some other element which is in the relation, it must be 2. So this element must be 2, otherwise it will break the definition of the function, because function has that restriction. If you have one input, it should only have one output. It should not be corresponding to outputs. That's what I read. If this A comma B belongs to this relation, and if A comma C belongs to this relation, whatever the relation is, then C is equal to B. Then it must be that this element, this B, is equal to C. Then only it will be a function. This is actually the mathematical definition. People usually write it. F goes from A to B. Now you know that going from A to B means Cartesian product. You'll take all the ordered pairs. This basically means this. A to B basically means you'll take a relation. And now by writing this F, you're putting additional constraints. So what is that constraint? The constraint is that one input should have only one output. One input cannot have two outputs. That's what I wrote. Functions are special type of relations. So whatever relations there are, so if A comma B belongs to R, if this ordered pair is there in the relation, and this ordered pair is in the relation, then it forces me that this B should be equal to C. If we have 1 comma 2 and if we have 1 comma 3, this is not a function anymore, because now it violated the rule of functions. How many of you understood the concept of functions? By definition, there is nothing to talk about functions now. So if you understood this, so you understood almost like 30-40% of functions, what function basically is. So now you have methods to find domain and then how to evaluate these functions. Okay, and we define different types of functions. Any questions? I'll pause the past. Let's suppose we have this computer vision program. That's nothing but a function. So what it does is it takes face as an input, और वहाँ पे एक complex mapping होगा. Let's suppose you'll use convolutional neural networks, or you'd use segmentation. You'll use different things in that. So it is a huge giant function, and probably you cannot comprehend the functions. That's why sometimes neural networks you cannot understand, because they are whole complex functions and you don't know what affects what, but there is some dependency. Okay, so that's why it's very essential to understand these functions from, I'd say, bare bone basics, from that nuts and bolts perspective. And you should not be thinking that this is defined in some mathematical lingo and we won't understand it. So the best part is to have a real world problem and then see it as a function. The whole neural network, the whole machine learning basically is trying to find a function. Many of you might know machine learning, so in that you will give some input and you try to give some output. Okay, so all the machinery that happens in machine learning, deep learning, whatever it is, so it is basically computing that function, coming up with that function, which somehow relates your input and which somehow relates your input to the output. Okay, if you have an image of cats, so what is that? That's bunch of numbers. It's basically set of pixels. So then you have a mapping in between. So you try to learn that function. Somehow this function is unknown to you, but by having a clever algorithms, by having some very nuanced novelty in these things, we try to find this structure and pattern in the things, and after that you get an output corresponding to that. That's all machine learning is. Machine learning is nothing, or machine and deep learning is nothing, but just finding a function, corresponding function. Okay, even if you see ChatGPT, if you see whatsoever tool you give me, I can show you that there is an underneath function into it. Okay, and these functions are pretty non-linear. We'll have a discussion on these linear, non-linear functions. But all the point of machine learning, deep learning is to find a function in which you give some input, it will give a corresponding output to that. Yes, Arsan, are you comfortable with the word relation now? Okay, so again coming back to this, so basically functions, why did I introduce it? The function is nothing but just a mapping from an input space to an output space. Now I started using space. Okay, why? Now also in the machine learning and this deep learning, we won't be having well defined things now. Okay, an image is not well defined. Let's suppose this 3 and this 3 are quite different, probably, and this 3, they're quite different, but you want to learn a mapping, you want to have a function which will map these things to 3. Okay, and which will map these things to 3, but all of these things are abstract, and that's what machine learning does. And in usually in deep learning, nobody understands it correctly. They don't know what is happening inside. They basically had just with these weights and biases. So we'll see that everything will be you'll get to know about these things once you know them. But please try to watch these lectures again. So when we learn the deep learning, come back to the function and see why have I introduced functions. So what I'm saying is you again try to learn a mapping. You want to recognize digits. So you want to learn a function, and then it should be giving a mapping for all these 3s. It should give an output as 3. And similarly in computer vision, you have a lot of problems. You have object detection, object segmentation, and things like that. So all these things basically are trying to learn a function and give some output corresponding to that. Now this function can be described as many things. I showed you a function can be described, and in your machine learning task or in your day-to-day task, this function can be defined in many ways. So one of the ways is basically algebraic way. So what is this algebraic way? You'll have this f of x gives you some x square plus 4, something like this. So this is an algebraic way where you put something and you get an output. And the second thing is it can be it can be shown numerically. This is A, and now we have B numerically. Everything is a function. Now if you look in the world, if you look around your world, and if you do not find functions, I'll say I'm not successful in explaining the functions. So everything you see is a function now. Okay, so how will be a function numerically described? Let's suppose you have temperature given, Celsius to Fahrenheit conversion. Okay, let's suppose in Celsius you have minus 10 degrees centigrade, it is 14 degrees Fahrenheit, and 100 degrees centigrade, I think it is 212 degrees Fahrenheit, and something like this. This is a table. This basically also is a function. This is an algebraic way of explaining function. This is numerically a tabular way of explaining the function. And one more important thing, is graphical way. Graphical way is you will be given some graph like this. Okay, this way, this is the function y is equal to x square. Okay, parabolic function. Okay, so usually you will be given either an algebraic way of explaining defining a function. It will be defined algebraically, or we can say a representation of functions. Representation of functions. So it can be represented algebraically, where you can just have a mathematical formula with these variables and these dependent and independent variables, and this is that way. And the second way is numerically. You will be given a table where a mapping is shown to you. And the third thing basically is a graphical way. Okay, that's what you do in machine learning. So this data will be given to you like this in the tables. Whatever it is, if it's an image, you just flatten out the image. So let's suppose you have an image. So image is like this. Image is nothing but a bunch of pixels. Okay, so bunch of pixels, and then you have a label to this image. Let's suppose this image is of dog, and then we have second image. It's again bunch of pixels. This image is of cat. Okay, this is of cat. The label is given to this. So how I can represent the table is like this. You have a table where you have pixel value. Let's suppose image 1, x1 I'll write. This is image 1. So I'll have pixel values 202, 241, or something like this. So the first image will be all a bunch of pixels, and the label here will be written as dog. And the second thing over here, x2, the second image, again it will have pixel values. Okay, let's suppose this is images of 28 cross 28. That means it has 28 pixels length and 28 pixels breadth. And this over here is cat. Now you see this is the table. And now you want to learn the mapping. The only part is how does this thing map to dog? How does this thing map to cat? And now you have to learn function in between. Okay, and this is our domain. This is our domain, and this is our range. Okay, and set of all animals will be our codomain. So we have a set of all animals that will be our codomain. So let's suppose we only are distinguishing between cats, dogs, and probably let's suppose some cows. So we have three animals only that we distinguish between. But there are all there are a lot of other animals also, but we don't consider them into our function. That's what that will be called codomain in our mathematical sense. Okay, everything in it, if it is given as a table, usually in math, in machine learning, you will be given a table. So usually we call this as a data matrix. Or if it is like, let's suppose you are predicting some weather in Bangalore, let's suppose. So weather in Bangalore. So what will be given? So you will have temperature over here. So weather can be, let's suppose, sunny, so rainy, and something else. Okay, so you will be given what is humidity, and the second component will be second feature or second input feature can be, let's suppose, wind speed, or maybe the temperature today and things like that. And the label will be sunny or something like that. You will have this data. You'll be given this data, and the only thing that you have to learn basically is the function over here. How this input, how this is my input, how this input is mapped to this output or to this label. This can be just one label, or it can be multiple outputs. And now in ChatGPT, what do you have, or in Midjourney? So you basically are giving a prompt. So prompt is nothing but text. That text is broken down. It's called as tokenization. So you'll have tokens. So when you give the ChatGPT the text, let's suppose you want it to give, let's suppose, some opinion. Let's suppose you ask it a question, what is the function? So what ChatGPT does is it will tokenize this first. It will basically take as an input. Take it as an input, then there is something called attention. So it will break down it like this. It will break it down into tokens. And these tokens, after applying the attention and these positional encoding and stuff like that, it will try to predict the next word. Okay, and just predict the next word basically is finding a function. So you give this as an input. So if I give this prompt as an input, what is the probability of getting the next word as this? Okay, this basically is again a mapping from this prompt to that prompt. Okay, and these are probabilistic algorithms again. Now if you again give the same prompt, it can probably, it does not always select the word with the maximum probability. It can select the word with the less probability sometimes. That's why sometimes they call it how much of randomness do you want in the algorithm. So if you want more randomness, you have to have that value higher. Okay, I think if you have used ChatGPT since the first release, they have given all these options there. But underneath the hood, what we are trying to do is we are trying to learn a function. Going back, just to summarize whatever we have studied so far is, we discussed what a function is. Okay, and function takes an input, and it gives us an output. Okay, and this input and this output, then we defined what is called as sets. And then we had a discussion on sets in which we defined what is the relation. And from this relation, we again came up what a function basically is. Mathematically, what a function is. Okay, so this is all in all that we discussed today. Okay, this is the whole thing that we discussed. Okay, I'll stop recording here. If you have any questions, you can ask me the questions.